Hello, this is Mrs. Schroeder. We are going to begin talking about Chapter 10, Section 3, with changes in enthalpy during chemical reactions. Our objectives today are this first part right here, explaining the principles of this big word called calorimetry. So in Section 2, we covered enthalpy changes if the temperature of the substance changed. In Section 3, we're not going to start talking about chemical reactions here. What's going to happen if there's a chemical reaction that happens during it? How does that enthalpy change in that system? So enthalpy, because we know from Section 2 that temperature is important, scientists have standardized the enthalpies of reactions. You have lists and lists you can look up. There's some in the back of your book that you can look up for standard enthalpies of different reactions. And they standardize things to this temperature of 25 degrees or 298.15 Kelvin is where they've considered the standard temperature for their reaction chemistry. This is not a gas law's standard temperature, so these do get confusing sometimes. The 25 is not used in any of the calculations we do. They're just going to state something like the enthalpy at 25 is, and give you an enthalpy, and that's just so that you know is it the standard temperature. Enthalpy changes in the chemical reaction are often stated as the enthalpy to form 1 mole of the products. Now, you know from balancing equations that sometimes we have coefficients, and we've never used fractions before, but now we're going to. So it gets a little confusing looking. So for example, I have hydrogen and I have bromine gas. I do this reaction, H2 plus Br goes to 2Br, and I measure this using a calorimeter. I'll show you how to do that in a little bit. And I figure this out. This is how many kilojoules I have. But that's how many kilojoules to make 2 moles of Br, HBr. So what they want to do is express it per 1 mole. So we'll actually divide everything by this 2. So we have 1/2 hydrogen, 1/2 bromine, goes to this. And notice, whatever I do to this, since I divided by 2, I have to do to the delta H also. So this divided by 2 is what gives me my 36.4 kilojoules at 298 K. So how do they figure out these delta H's? How do they give me these formulas and know what the enthalpy change was? Remember, enthalpy is only measured through a change in the system. But I have to have a standard system so that I can measure it against. So we use this thing called a calorimeter. In calorimetry, the principle behind this is the law of conservation of energy that says energy is never created or destroyed. It only changes form. So if I want to affect a change in a reaction, and it gives off enthalpy, then something else has to gain it. So I use that principle in my calorimeter to collect the energy, absorb that energy from the reaction, and measure it by change of water. How much did the water take in? Because that energy is being given off as heat. So again, energy that's released gives us a negative delta H. If delta H is positive, it's absorbed by that system from the surroundings. The calorimeter will actually measure the change of a standard temperature of water, which is my Q. What does my Q change to? NC delta T. And then I apply this principle. Heat lost is the negative of the heat gained. I could say it this way. Heat delta H lost is equal to the absolute values of delta H gained. What I'm talking about is the amount. Whatever amount left that system is the amount the water gained. So the negative sign just changes the direction. Now instead of talking about how much is the negative delta H going out of the test tube or out of the reaction, now I'm looking at it from the water. I'm going to jump into the water and look at the water, and the water is absorbing it, so delta H should be positive for the water. So really this sign just means it's the opposite of the direction changes of the heat. So direction of heat changes. Okay, so what a calorimeter looks like. This is a typical calorimeter that a scientist might use. It's called a bomb calorimeter because it's set up to burn things. And you can see there's an insulated outside container here. There's water on the inside. The sample is first placed in the dish, and then it's ignited. They use a coil right here that they can add some electricity to and make it start to burn. Once it starts to burn, it gives off energy, or it takes in energy. Usually burning means giving off, so the energy is going out of here. Once the energy is being released to the water, what's going to happen to the water? Temperature is going to go up. So I use a thermometer over here to measure how much the temperature changes. And then based on the temperature change, I use the Q equals NC delta T for the water to calculate the heat gained by the water. Set that equal to the opposite or the negative of the heat lost, and that's one way to calculate the actual energy for that system. Okay, example here that's given. And this is the one, I think, from the book. Certain calorimeter has a mass of 220 grams, so a heat capacity of 4.069 joules per gram Celsius. So if you see this per gram, now they're using the other equation, mCp delta T, because this is given off as Cp. So be careful with these problems. They do start to switch back and forth on you sometimes. We've been learning about molar enthalpy and molar using molar heat capacity with joules per mole. They may throw you back. So always look at this unit and decide if I'm going to change or not change to my moles. So I'm going to take this is my reaction happening in here in my bomb calorimeter. I can figure out the heat that the calorimeter gains. mCp delta T. This is the mass of the water. This is the Cp of the water. And this is the temperature change of the water. And you're going to get big numbers. That's okay. You should see big numbers. You don't need to put decimals down, but you will get to big numbers. Now, the heat produced by the reaction is equal to the heat gained by the calorimeter, the opposite of. So change the sign of that number. Okay? Q of the reaction equals negative of that number. If I want to know the heat of combustion, it's asking me to find the heat of combustion in joules per mole. So how do I find joules per mole? I'm going to have to take my sample. My sample was a 3.5 gram sample of carbon. So 3.5 grams of carbon, divide it by its molar mass to get my moles of carbon. So the heat generated per mole of carbon now is this joules per mole is my units, which is this number and this number. Joules per mole. Take this number, the 117,000 divided by 0.2914, and I get a very big number. Often we're going to switch that to kilojoules just to make it a more manageable number. So let's do one on our own, or one together here. 5.4 gram sample of butane burned in a bomb calorimeter. The water increases in temperature. I need to find out the molar enthalpy of combustion, so delta H per mole. So first thing, let's look at the Q of the water. And I'm given, for water, I'm given mass. Actually, I'm given volume. Okay. Remember that mass over volume equals density. For water, that equals 1 gram per mil. So 1,000 mils is equal to 1,000 grams of water. And that's only for water. So I'm going to go ahead and change this to 1,000 grams of water. Sorry, mCp delta T is what I'm looking for. Cp for water is given 4.18 joules per gram K, given in the problem. Delta T for the water, final, which is 87.1, minus initial, 22.4. And when I do that, it's going to equal 64.7 degrees Celsius. So 64.7 degrees. When you multiply this out, 1,000 times 4.18 times 64.7, I'm going to get a big number, 270,446 joules. That's how much water, or that's how much energy was gained by the water. That many joules of energy. Now I'm going to set my Q of the butane equal to the opposite of the QH2O. So it's going to equal negative 270,446 joules. And they ask me to find enthalpy per mole. Remember, if the pressure does not change, so the pressure is constant, delta H equals Q. So this also equals delta H. But I want to know delta H per mole. I have a 5.4 gram sample of butane. Butane is C4H10. I calculate the molar mass of butane, 4 times 12 plus 10 times 1.008, and I get 58.124 grams per mole, which is going to equal 0.0929 moles of butane. So my enthalpy, molar enthalpy, would be delta H per mole, or negative 270,446 joules divided by 0.0929 moles. And that's going to equal a very big number, 2911152 joules. Again, it's too big for me to really want to write down, so I'm going to change that to kilojoules, dividing it by 100 or 1,000 to get to kilojoules. And that tells me my molar enthalpy, kilojoules per mole. Okay, so it's a lot of steps to do one of these problems. The principle behind it, again, is heat lost equals heat gained. Now, nutritionists use calorimetry. You wonder about all those energy calculations, how many calories are in your granola bar, how many calories are in your piece of pizza. They do this by burning food, basically. They've got a nice fancy calorimeter, bomb calorimeter. This is an example of what one might look like in a nutritionist lab. And they report energy content in calories, not joules. The conversion, 1 calorie, is 4.1858 kilojoules. So energy in your food is essentially what we've been calculating for energy that it takes to burn butane. It's all the same. Energy is energy no matter where it's coming from. So I can do calorimetry with food.